So thank you. I'm going to build on the nice talk by John and tell you about how to bridge the gap between optimal transport and something called maximum mean discrepancies with Sinkhorn divergences, so a type of distance based on a regularized version of optimal transport, and we'll see how this fixes some of the statistical and computational issues of optimal transport that John just presented. So the motivation here is to be able to compare probability measures in a variety of settings that can range from continuous to discrete measures. And this is motivated by several problems in machine learning. So here I'm going to focus on problems that are that can be defined as minimization problems over the set of probability measures. So when you consider two discrete probability distributions, you may consider the problem of measure quantization. So you have this orange point cloud here that represents a discrete probability measure in some space, and you want to summarize this large point cloud by a smaller point cloud. And so this problem can be formulated as minimizing some notion of distance between these two discrete measures. And the question of finding a good notion of distance between the measures to do this minimization problem is crucial. Okay, you want to follow some sort of gradient, I mean the gradient of that distance, so that you get a good summary of your large data set. And alternatively, you can consider this problem in a semi-discrete setting. So this is motivated, for instance, by generative models that were introduced also this morning in a nice talk. So you have this high-dimensional point cloud that has a known probability distribution beta, and you want to find some probability measure that is going to be parameterized by a parameter alpha, and you want to find the parameter alpha that is going to minimize, again, the distance, in some sense, between your model measure alpha theta and your unknown data measure beta. And so once again, you want to be able to follow the gradient of that distance to have a model measure that fits your data set very well. And so the crucial question in these problems of minimizing over the space of measures is what notion of distance do you use? So I'm going to review the main notions of distance that are used between measures, and then I'll talk about our notion of distance that we came up with co-authors. So probably the most well-known notion of distance between measures are phi divergences that were introduced in the 60s by Cesar. And they are they require to use a convex function phi that you're going to use as a test function to compare the ratio, the odds ratio of your two measures, alpha and beta. And the best well-known is the KL divergence, which uses the function phi x log x. And so you're going to look at the distance between alpha and beta by looking at the log of the ratio of the two densities. And this has several shortcomings when you want to use this notion of distance between measures in the learning framework. So consider this very simple problem where you have a target measure alpha, that is this blue Dirac in 0, and you have this this sequence of measure alpha n that is simply a Dirac located at 1 over n. And so you see that when n increases, your orange measure is getting closer to the blue measure, and so you're converging in some sense to your targets, that is the Dirac at 0. But if you just look at the KL divergence between your target measure alpha and the sequence alpha n, you're always going to get a KL distance that is going to be plus infinity. So it means that when you look at this problem, so for instance, if you want to get some signal that you're getting closer to your target measure, well, the KL divergence is not a good notion of distance to use, because it gives you no way to know where to go to get to your target distribution here. And this is formalized by the notion of metrizing weak convergence of measures. So what is weak convergence? It essentially means that when you integrate any continuous bounded test function against your sequence of measures, it converges to the integral over the target measure. And this is a natural formalization of what I was showing you here with these Diracs, is that it is a good way to tell that the measures are getting closer. And so you want a distance between measures that is going to be equivalent to metrizing to converging in the weak convergence sense. And that is not the case of phi divergences. So one alternative to KL divergences that has this nice ability to metrize weak convergence are maximum mean discrepancies that were introduced by Arthur Gredin and co-authors a few years back. And so they are based on the notion of reproducing kernel Hilbert spaces. So for those of you who are not familiar with RKHS, they're essentially a Hilbert space of functions that is endowed with some kernel function k. And so you can say that any function that is in this RKHS can be written as the scalar product of some representer of the function f against that kernel function k. And this kernel representation property allows you to do a lot of computations in a very elegant manner, and so it simplifies a lot of things. And this, in particular, allows to define another notion of distance between probability measures. And that's what we call the maximum mean discrepancy. So it's most generally based on what are called integral probability metrics. Integral probability metrics essentially consider a set of test functions f, and they look at the maximal gap of the integral over alpha of that test function versus the integral over beta of that test function. And so depending on the test set that you use here, you're going to get different notions of distance. So for instance, if you use the set of bounded functions, of functions bounded by 1, you get the TV norm. If you get the set of 1 Lipschitz functions, you will get the 1 Wasserstein distance. And in the case where you use the function of norm 1 in that RKHS, you get what is called the maximum mean discrepancy. And you can leverage here this scalar product formulation involving the kernel k to rewrite this thing. So the soup is known in closed form. And so you can just rewrite this integral probability metric in a very simple form that just includes expectations with respect to product measures of the kernel function k. And so this is what is known in the literature as maximum mean discrepancy. And you can see that it's a very simple formulation that just requires evaluating expectations. And so you can just compute it from samples of the probability measures by just replacing the expectations here by empirical expectations. The other notion of distance between probability measures that one can use is based on optimal transport. So you've already had an extensive presentation by John, so I'm going to skip over that one. But essentially, you want to learn a coupling that is going to map your first probability measure to the other. And you want to find the coupling that does that at minimal cost. And the solution to this optimal transport problem is what we call the Wasserstein distance. So this is the Kantorovich formulation of optimal transport. So you're minimizing over the set of all couplings that have marginals alpha and beta, the total cost of moving your mass from alpha to beta. And the notion of cost that you use here is very important. It's going to be essential for to have a good geometry for your problem. But in the case where the cost function that you use is the sum power of the Euclidean distance, you get something that is a real notion of distance between measures. Okay, so how to choose between optimal transport and MMD? So we can compare them from two perspectives. So the first one is the sample complexity, which corresponds to how well you can estimate your distance from samples of the measures. So for MMD, you have a sample complexity that scales as 1 over square root of n, so you don't suffer from a curse of dimension. It's pretty efficient to estimate MMD from samples. Whereas for optimal transport, as John stressed before, you have a curse of dimensions, you have an exponentially bad dependence in the dimension. And there are some things you can do about it, like assume some lower dimensional structure of your measures to improve that bound, but you still get something that is pretty bad statistically. From a computational perspective, so meaning given samples, how fast can you compute this? Well, for MMD, if you remember before, it was essentially computing expectations over product measures. So if you're looking at expectations with samples from these measures, you get something that scales as n square, where n is the number of samples of your measures. And again, if you consider optimal transport, solving the optimal transport problem between two samples of size n, so two measures with size n is going to scale as n cubed log n. You have to solve a linear program, so it's much more costly than computing the MMD, which is just a closed formula. So when you look at this table, it seems that using optimal transport for any sort of learning problem is pretty hopeless. So why did people still try to use this? Well, it has a nice geometry. So if you remember the quantization problem from earlier, so I have this this point cloud here that is separated in two different point clouds. And so this orange thing is my target that I want to quantize using the blue points here. And so I want to follow the gradient of MMD in order to minimize the distance between my orange point cloud and my blue point cloud. So here's what happened when I follow the gradient flow of MMD. I get my blue points that kind of blow up everywhere, and then they have really a hard time converging back to these orange point clouds. So eventually, it gets there, but it's pretty slow. And I have some points that kind of get lost behind. When I use optimal transport, when I use optimal transport, so here the speed of the video is kind of slow, but you can see that the points really get matched where you want them to go straight away. Okay, there's no blowing up and then coming back. The gradients are really efficient and really get you where you want to go. So I should have used the same time scale for both videos. That's I'm sorry about that, but it's getting there. In a much more efficient way than MMD, even though this isn't what it looks like. But essentially, the message of these two videos is that optimal transport gives you better gradients than MMD, and so for a minimization problem over the space of measures, having good gradients is crucial. Okay. Okay. So here's a quick summary. Okay. So MMD points that lag behind because of bad gradients, and Wasserstein really spot on good gradients for minimization problems over the set of measures. That's still so that gives us we want to find a way to be able to use optimal transport, but in a way that is more computationally efficient and that has better statistical guarantees. And so the solution to that, I'm going to argue, is entropic regularization of the optimal transport problem. So if you recall the formulation of the Wasserstein distance, which is this minimization over the space of couplings, Couturi in 2013 suggested to add an entropic regularization to this minimization problem. And so you just choose a penalty epsilon, and you penalize the Wasserstein distance by the entropy of your coupling with respect to the product of the marginal measures. So what does it do? If you remember the coupling matrix from earlier, so it tells you if you visualize here one measure in one dimension on the left and one measure in one dimension at the top. It tells you if you take a point in this measure here, where are you transporting it in your second measure? And you know that when you take the standard optimal transport problem, so the non-regularized transport problem, in the case of continuous measures in 1D, you would have a transport map here that is concentrated on a line. And so for a small regularization parameter, that's pretty much still what you get, but the more you regularize, the fuzzier your assignment is going to be. Okay? If you look here at the large regularization, if you take mass at some place in your source probability distribution, you get a whole area here that you're going to transport in the second probability measure. And so this regularization parameter is going to give you fuzzier assignments. And so it's just a way to regularize the problem, and in particular, it's very enjoyable from a computational perspective. If you look at the dual formulation of optimal transport, so this is the convex dual, you move from minimizing over the space of couplings to maximizing over the space of continuous functions. And so you have two functions here, U and V, that we call the dual potentials. They are each associated to one marginal constraint. And so if you look at the dual problem here, you still have a constraint problem, a dual constraint problem, where the sum of your two dual potential has to be smaller than your cost function C. But if you regularize the problem, instead of having this constraint that U and V has to be smaller than C, you have an exponential penalty on that constraint. So it replaces the hard constraint by a smooth version of the constraint. So it makes the problem concave in each of the variables, and so much easier to solve. And it also has the nice property that it can be expressed as the maximum of the expectation under the product of your marginal measures of some functions. And so you can then leverage different properties or use stochastic optimization to solve this problem. And so regularization is a kind of a magic tool here. And so as I mentioned, the problem becomes concave in each of the variables, and so naturally you can think of an iterative algorithm to solve this problem, which is going to consist in alternating between optimizing over one potential U while fixing the other, and vice versa. And this is what is known in the literature as Sinkhorn's algorithm. So if you rewrite the optimality conditions in the case of discrete measures, you get an algorithm that consists in essentially just doing vector matrix multiplications. And so this scales, if you have measures of size n, this scales as O of n squared, which is the same order of computation as MMD. Of course, there is no free lunch here. If you take a regularization parameter that goes to 0, so if you're getting closer to the true optimal transport problem, you have a convergence rate that gets really, really bad. And so you recover this problem of bad computational estimation of optimal transport. OK. So we moved from computing optimal transport in O of n cubed log n to estimating transports in O of n squared. So that's a big improvement from a computational perspective. It also has some nice properties if you want to use transport for a learning problem in the sense that this whole Sinkhorn algorithm is fully differentiable. So you can compute transport using Sinkhorn's algorithm and then backpropagate through the whole procedure using your favorite automatic differentiation algorithm and get the gradients of that thing. And so this allows you to use the entropic version of optimal transport for a wide range of applications. So you can get, for instance, a differentiable version of sorting by leveraging the fact that optimal transport in one dimension is essentially just sorting a vector. You can also get differentiable assignments by looking at the assignment matrix that you get from optimal transport. You can leverage it to do differentiable clustering And more importantly, you can use it to learn with a regularized Wasserstein loss. And that's something I'll come back to later in the talk.
So when you want to use this differentiation, do you run Sinkhorn for a constant number of rounds?
Yeah. Yeah, because having a while thing wouldn't make it differentiable. So usually, yeah, fix the number of iterations. Okay. So we've seen so far how this entropic regularization solves the problem, the computational problem of transport. Now I will argue that it also solves the statistical problem of transport. So the sample complexity of the distance between measure reflects essentially how good your approximation of the distance is when you approximate it using samples of the measure. So we know in the case of transport, if we use here empirical measures for alpha and beta instead of the measures themselves, we get something that squares as n to the -1 over d. That's the curse of dimension that we've seen previously. For MMD, as I said before, if you estimate MMD from samples, you get something that scales as 1 over square root of n. And so we decided to investigate the sample complexity of regularized transport. And so a very recent result that I got with co-authors, and that was refined a couple of months later by John here and Gonzalo Mena, is that essentially the sample complexity of transport is going to, at one end of the spectrum, be the same as transport, so have a curse of dimension, and at the other end of the spectrum, have a sample complexity that is similar to MMD. So I'll just skip the general statement and move to here the asymptotics. So if you have a small regularization parameter, so if you're getting closer to optimal transport, you get a rate that still has a bad dependence in the dimension here. On the other hand, when you get a regularization that goes to infinity, you recover a rate that is similar to MMD. So it tells you that if you get a large enough regularization, you don't suffer from the curse of dimension that is inherent to optimal transport. That gives some hope when using this regularized version of transport in high-dimensional learning settings. Okay, so now that we have managed to solve, in a way, the computational and statistical problem of optimal transport by using this entropic regularization, we want to see what happens when we use this for this quantization problem. And so here's what happens. Not really what we wanted. You can see that the blue points here, instead of really recovering the support of the orange point clouds, just concentrates in some locations. And so, sure, we got something that was much faster than computing transport, but we don't get something that is quite satisfying. And so, why is that? It's because this entropic transport model is essentially assuming that you have some Gaussian noise on your data points. So that's something that John and Philippe noticed, is that when you're minimizing the Wasserstein distance with regularization parameter epsilon between some empirical measure and some model measure, it's the same as doing maximum likelihood in a model where you have Gaussian noise of variance epsilon. Okay, so when you're doing this minimization, so here's the effect of entropy. So when you're doing this minimization problem with some regularization parameter epsilon, it just assumes that everything, that all these orange points have been perturbated by some noise of level epsilon. And so, of course, that's why these blue points are concentrating here kind of around the mean of your point cloud. It's because they assume that this is just noise and that your true underlying measure here is more concentrated than what you see on your data points. So this can be a good thing when you assume that your data is very noisy, but in the general case, that's not really what you want. Okay, you want to be able to have some distance between measures that will recover the whole support of your target. So how can you somehow fix the effect of entropy? So the idea that we came up with was very naively to debias the regularized transport by adding these two terms to ensure that when you take alpha equal beta, you get something that is equal to 0. Okay, you can check it immediately here that if you take alpha equal beta, you're going to get something that is... Sorry?
Your battery.
Oh. I hope it's going to hold, or if anyone... Oh. Is it the...
USB-C, is that right?
Oh, no, I have a MagSafe, if anyone has one. Sorry. No, I have an older one. Yeah. Okay, so hopefully I'll get to the end of my talk here. Right, so we introduced these, what we call Sinkhorn divergence, which is essentially regularized transport minus these two debiasing terms to ensure that we have something that is equal to 0 when both measures are equal. And aside from this naive idea, we can actually see that it has nice asymptotic properties in the sense that when you take the regularization parameter that goes to 0, these Sinkhorn divergences converge to optimal transport. But when you take the regularization parameter that goes to infinity, oh, thanks. Your Sinkhorn divergences converge to MMD, where the kernel function of your MMD is going to be minus the cost that you use in your definition of optimal transport. So these Sinkhorn divergences here have an interpolating behavior between optimal transport and maximum mean discrepancies. So of course, for this thing here to be a valid distance, we need to ensure that this thing, like minus c, gives a positive definite kernel. And that is the case when the cost function is some power of the Euclidean distance that is strictly smaller than 2 here. And then the MMD in that case is called in the literature the energy distance. Thanks. Okay, and so, one other thing that I didn't include in the slides, but the Sinkhorn divergence also has the nice property of being positive definite. So it's obvious that it's equal to 0 when alpha equal beta, but it's harder to prove that it's equal to 0 if and only if alpha equals beta. And this was proved recently by colleagues at ENS. Okay, and so now if we use this, the biased version of regularized transport for the quantization problem, what happens? Well, we fixed it in a way. We recover the full support of the target measure. And if we look at the dynamics of the gradient flow, see if I can. It's kind of, the dynamics is also kind of interpolating. I mean, not kind of, it's really interpolating between the dynamics of transport and the dynamics of MMD, in the sense that your points kind of blow up in the beginning, but not too much, and they get pretty fast to where you want them to go. So this interpolation property is actually kind of funny if you look at it, because it's first you just notice it in terms of the value of the distance itself, but you also have it in terms of sample complexity, and you also have it in terms of gradient flow. So it's so you can say that the Sinkhorn divergences are really doing a mix of MMD and optimal transport and pretty much all the learning aspects that you can think of. Okay, so if you recall here what was happening for MMD, this big explosion with points that were very slow. So if we summarize the different notions of distances, of distance that I've introduced so far, so here, the top middle, you have the regularized transport, which has the issue of concentrating all your points at the middle of your target. Here, energy distance, so it's MMD with the kernel being minus the Euclidean cost. you have the points that are lagging behind in the more extreme parts of the target. If you take the Sinkhorn divergence with the same regularization parameter here, you get something that recovers the support very well. If you take the Sinkhorn divergence with a very large regularization, you converge to MMD, and so you start to have this problem again of the points that are lagging behind. Okay, so now that I've hopefully convinced you that the Sinkhorn divergences are a good notion of distance between measures to solve these minimization problems, we can use them for inference in generative models, for instance. So generative models are a class of problems that can be defined as measures that are defined as the push forward of a low dimensional measures through parametric function g theta. And so they usually are used to represent measures in a high dimensional space that are going to be supported on a lower dimensional manifold. And these models have no likelihood, so you can use the standard maximum likelihood framework to estimate the parameters of your measure theta. So what we propose is to use the Sinkhorn divergence here as a notion of distance between the model measure here from the generative models and the unknown measure of the data beta. And so in the framework of generative models, we only have access to samples of the target measure alpha and of the target measure beta of the data and the model measure alpha theta. And so we're going to solve this problem using gradient descent by doing two different approximations. The first one is that we approximate the measures alpha, theta, and beta by empirical versions of these measures using samples. So that's the first approximation. And the second approximation is that we're going to approximate the Sinkhorn divergence by doing a fixed number of Sinkhorn iterations. And so that gives us a differentiable approximation of the Sinkhorn divergences between the data and the model. And by differentiable, I mean that we can compute its gradient by using backpropagation. So it's very easily done over a GPU, and it allows you to use it for very complex models where G theta is your favorite generative neural network. And so this gradient is computed automatically, and you can just put it in your gradient descent routine. So here's a it's in French for your pleasure. So it's the routine here. You have your generative models that is going to spit out a bunch of samples according to your current model alpha theta. You have your points from your data set here, beta. You compute the cost matrix between the samples from your model and from your data set. And then you run a few iterations of Sinkhorn's algorithm, and you get your proxy for the distance, and you just backpropagate through this whole graph to get your gradient. And that's how you estimate generative models in practice using Sinkhorn divergences. So before showing you the results with complicated neural networks, it's just a proof of concept in a very simple 3D model that is still a generative model. So we have here this blue point cloud that is points that are generated uniformly inside of an ellipse. And so we want to learn the covariance in center of this ellipse. So it's not a Gaussian, it's really an ellipse, so something with a hard threshold. And so this ellipse is a generative model in the sense that it's a deformation of a uniform sample in a ball, and so you just deform the sample to get the ellipse. And if you look the regularized transport as a notion of distance here for your generative model, you recover the problem that I showed you earlier in the quantization problem, in the sense that your ellipse is going to be completely flat. So it assumes that all the variations in the ellipse are just noise, and so it just estimates something that is just at the mean of your ellipse. But when you debias with this Sinkhorn divergence, you recover the right centers and covariance for the ellipse. And here's a comparison with the energy distance, so the MMD based on the Euclidean distance. Here are the estimations of the centers of the ellipse and the covariance, and so you get better estimation using Sinkhorn divergence than MMD. So here I was dealing with simple problems in 3D, so the natural notion of distance to use between my data points was the Euclidean distance. When you're using generative models in a high-dimensional setting, it's more complicated to know what notion of what cost to use between your data points. Okay, if you take two images and you look at the Euclidean norm between your two images, it's not going to be a good indicator of whether your images are representing the same thing. So one idea is to learn the cost function in an adversarial way. So you take a cost function here, C phi, that is going to be the Euclidean distance in some embedding space, that is where the embedding is parameterized by a neural network. And so your optimization problem now becomes a min-max problem, which is very similar to what you have in GANs. And so you're still trying to minimize with respect to the parameters, so the Sinkhorn divergence with respect to the parameters of your generative model. But now you're also maximizing with respect to the parameters of your cost function. So here the cost function acts as a discriminator, if you think of it in terms of GAN models. Okay, and so when you learn this cost function, you are then able to use this for image generation purposes. So here are my experiments. So I'm not a specialist in GAN, so I don't really have anything impressive to show, but some people in OpenAI, I forgot to cite them, but have pretty impressive images of what you obtain with optimal transport versus other distances. But here, doing very simple experiments on C410, we have better inception scores using optimal transport rather than MMD. Okay, so to wrap it up, the message that I hoped to carry today was that Sinkhorn divergences are a great notion of distance between measures, especially when you're trying to do minimization problems over the space of measures. They are a way to debias the regularized Wasserstein distance, and they have the nice property of interpolating between optimal transport for small regularizers and MMD for large regularizer. And they kind of get the best of both worlds in the sense that they get the good geometric properties from optimal transport, in particular very good gradients. But they also break the curse of dimensions for epsilon large enough, and they're easily computable for implementation in a variety of machine learning tasks. Thank you for your attention.